Great to see everyone here, and really excited to deliver this, what is going to be a keystone talk in this review of or coverage of materials on double categories, Lex double functors, and double models on double theories. This material, as I've described before, is of great strategic importance to our lab. And really, as before, I'm going to be unpacking source material, aping material from a combination of folks, particularly strongly Kevin Carlson, Evan Patterson, Michael Lambert, but occasionally potentially drawing on materials from Durrett Pronk or John Buys. So we've covered in past sessions, motivations for this work, and those motivations are going to, at least one of those motivations will come through very strongly within this session with the particular exemplar or example of causal loop diagrams. We've also covered in past sessions the basic ideas of extending categories to multiple dimensions per these notes from John Buys, where double categories are have a set of very nice properties that we're going to be mining. And we've covered the basics of those double categories. The fact that they include not just objects, but strict vertical arrows, horizontal pro arrows that are not strict, instead, which are associative up to a horizontal, so horizontally associative up to isomorphism, and unital only up to isomorphism. So when we compose them horizontally, compose a pro arrow horizontally with the unit pro arrow, say in this case for B, we get back something that's not exactly that original pro arrow, but something that's isomorphic to it. And we saw in our last session yesterday, we saw a set of examples of this with rel, with the cospan, double category of cospans, and finally, and of key importance here, the double category of spans. And we're going to be drawing very strongly on that last one in today's sessions. So we've covered in past sessions these basic properties of double categories. I'm not going to go over, and these examples. This example of spans, if you haven't seen it, it's worth reviewing prior to this because it will explain a lot of the specifics. Those who have seen it will be able to immediately draw on that for the key understanding of why we get, with double theories, objects mapped to categories. And we'll be able to get immediately useful understanding of how to use Cat Colab for encoding compositionally things like causal loop diagrams. In fact, for that particular example, using a beautiful example presented by Kevin Carlson. Okay, so the key element that we're going to need to draw on is one I mentioned at the beginning of our, at the end of our last session, and it's a Lax double functor. Lax double functor from one double category to another. And like functors, just as functors for normal categories map objects to objects, morphisms to morphisms, sort of like to like, as it were, but with a certain coherence that ensures that the mapping of morphisms respects the source and target, and honors composition and identity. Here we have a likewise mapping in the basic regards of objects in category D to objects in category E, vertical arrows in category D to vertical arrows in category E, and pro arrows in category D to pro arrows in category E, and two cells, these double cells in category D to double cells in category E. And I think everyone here is generally familiar with those terms and why we've broken it up into these two components, reflecting the two categories present in every double category. But just as for regular category, this mapping has to honor certain relationships. It has to honor them here. The particularly easy relationships that it needs to honor are the vertical ones, where it's strict. So this functor, these functors, honor exactly on the nose vertical composition of arrows. So we can compose, say, two arrows vertically within the source category. Okay, just what I needed. Within the source category, and then map them over, or we'll be guaranteed to get the same thing as mapping each arrow over to the target double category and then composing there. Same thing with cells. We can compose them vertically in the source double category or vertically in the target double category interchangeably. They're guaranteed to be the same when mapped. So the image of the composition is guaranteed to be the composition of the images, to use kind of a pithy way of putting it. Where things become more flexible, and where they need to be more flexible, given the definition of double categories, is with horizontal composition. So here, with horizontal composition, we have some laxness. And this is needed. It would be, as Kevin Carlson observed, somewhat unnatural if we didn't have looseness here, because after all, you may remember that in a double category, associativity horizontally is only guaranteed up to isomorphism. And indeed, composition with identity horizontally, the uniters, are only honored up to composition. And so we need, from a lax double functor, this extra flexibility. But here, when we consider the composition of two cells, the image of the composites is not merely isomorphic. It's not guaranteed to be isomorphic to the composite of the images. So again, F is this double functor. Rather, it's only guaranteed to have a morphism from this composite of the images to the image of the composite horizontally. So this is for composition of two arrows. And that's going to play a key role in double theory about why lax double functors describe these models that can allow us to capture composition in the target category. So here, the composition of the images of two arrows does not directly give the image of the composites. Rather, there's a morphism between them, which gives us this flexibility to specify what the composite is for two arrows. When we hit it with the lax double functor, we can specify what, if we have an arrow x to y and another one, a pro arrow x to y and another one pro arrow from y to z, we can, as it were, choose a compatible, it has to be within constraints, pro arrow from x to z in the target. And there's a similar thing for uniters, mapping from the identity on the image to the image of the identity. These are morphisms. Now, I could dwell on the naturality of the laxator in of the compositors. I'm going to use the terms interchangeably. So given two cells, alpha and beta, we can either lift alpha and lift beta horizontally, and then use the compositor or laxator here to map those images of those two morphisms at the bottom here, M prime and F and N prime, to compare that to map it to the image of the composites of these two morphisms. Or we could of M prime and N prime, or we could hit it with the laxator first to get this mapping to the sort of composite, or the mapping between the image, the composite of the image to the image of the composite, and we can end up then lifting the composite of these two cells. And this turns out to be a key property that lies behind the ways in which models of these lax double functors serve as models of double theories. Okay, so I want to remind us that for lax double functors, horizontal composition is only up to this comparison cell, this one here, and for uniters, horizontal composition with identity is only up to a comparison cell. Vertically, it's all straight. These are also not just isomorphism; they're up to this sort of cell, which Kevin Carlson describes as a map from these the composite of the images to the image of the composite, and I'll often fall into that too. So we're going to be using as our example of encoding a model of a double theory causal loop diagrams, and I think it'll be quite instructive. You will likely remember, everyone here, that we could, using a C set, I'm putting aside the attributed C set we used with some attributes for labels, we could describe a causal loop diagram, primitive causal loop diagram, as having an object variable, an object L plus and L minus, and when we map those over into set with a C set, right? As a traditional model of this theory, we will get a set of variables, a set of plus arrows, a set of minus arrows, and these morphisms here, say from a plus arrow to its source variable, would turn into a function that maps from the set of plus links. For each of them, it would specify the source variable for that link, right? There should be a familiar concept to you when we did that for plus and minus. And we had a quite nice little encoding of a causal loop diagram. So where we're going has some common threads with that, but it's much more powerful yet, what's enabled here. And I'm gonna show you what it does, and we're going to walk by why this happens, why this is what results. We're going to encode a primitive causal loop diagram with a single object, not three here, not these three, but just one. And we're going to encode the presence of plus links with an identity pro arrow from V to itself, from the single object to itself, U sub X. And we're going to encode negative links with another pro arrow, not the identity one, from V to itself, which we're going to call, following Kevin Carlson, who I'm aping in this, is Z sub 2. Okay. And there's going to be an identity, just as all objects in double categories have an identity, vertical morphism, a strict one, or that's there, but we're not going to use it here. That would turn into a functor, it turns out, when we map it over. But the lax double functor here, this encoding of the model for this theory, so this is the theory, kind of like our schema, as it were. It's mutatis mutandis. It's going to map over this schema. This theory is going to map over to a family of categories. That family of categories is going to be populated by one category for each object. In this case, there's only one object, an object that's over here. And that object, its job in life, it embodies, it is to represent the causal loop diagram. It embodies the causal loop diagram, this thing to which the object maps, this category. It embodies the particular causal loop diagram. So if we wanted to encode this causal loop diagram, we would encode it not as 3 tables as we did here. No. We'd encode it as 3 objects in this category with 3 morphisms between them that are encoded as images of Z2 with minus signs. Secretly, there are little plus morphisms from each of these variables to itself, 3 of them, that are associated with this identity pro arrow, 1 for each of these objects. Okay. So this object turns into a category, and these morphisms involving the category here are turning into describing these links between these variables. V used to turn into a set of disconnected elements, just grains of sand totally disconnected to each other, a heap, as Herder would have called it in continental philosophy. A heap of a set of disconnected things is what V used to turn into for C sets. Instead, it turns into a category, something which can describe connection, and the connections are each connection comes from the mapping over via F of an arrow here, with these 3 all coming from Z sub 2 because they're all minus links. And as a category, these can compose. And the rules of composition will be given by this compositor. The rules that when we compose a plus and a minus, we get a minus, a plus and a plus, we get a plus, a minus and minus, we get a plus. That's sort of where we're going, big picture here. So in this case, so in general, we get a Lax double functor will give us a family of categories from our theory, our particular theory. Here we only have 1 category because it has 1 category per object. And the vertical arrows here will turn into functors between these categories. Here there's only one from V to itself, so it turns into a functor from this to itself. That's the identity. Not so interesting. But in general, this is going to be in a double category called prof. So this is picking out or targeting or embedding in 1 category in this double category called prof, whose denizens, whose members, whose inhabitants of prof, whose objects are categories. Think of it as kind of the double category theoretical version of CAD. Each of these is a category. And they have vertically functors between them, and they have horizontally profunctors between them. And I've taken the liberty here of saying, well, this is a vertical arrow, but I'll draw it horizontally from this guy to this guy. I'll say there's a profunctor from this guy to this guy and a functor as well. So this is a double category of categories. We are, any given theory is going to be mapped by a model to a family of categories embedded in this prof category. And that family of categories will have profunctors between them in general. 1 for each pro arrow, it turns out. And they will have functors between them according to the vertical arrows in this source category. Note that these things here in prof are categories. They're not double categories. It's a double category of these categories. We have objects. We have vertical morphisms that are functors. We have horizontal morphisms that are pro arrows. And we have 2 cells, which are natural transformations. But these individual things are categories. This is a category, not a double category. Okay. So that's where we're going. I want to unpack this example following the masterful lead of Kevin Carlson. Okay. So we're going to actually walk through taking this category, which he's drawn here, excuse me. He hasn't bothered drawing, per normal category practice, he hasn't bothered drawing the identity morphisms, the identity pro arrow he hasn't drawn. He hasn't drawn the identity arrow, vertical arrow, but he drew the Z mod 2. I should have the Z/2 there. Pro arrow like this, okay, which he called Q. And we're going to see how we can encode how this functor, together with this double theory, specify the rules of engagement for this category, what the objects are, what the morphisms between those objects are, why they have plus, which of them have plus signs, which have minus, and how they compose. Like a minus and a minus turn into a plus. So that's where we're going. Okay. So to understand this, though, I want to make sure everyone remembers spans, because when we encoded things with C sets, we mapped from a schema category, create a presentation of that schema, we mapped it into set. When we did that, we got these disconnected bags of elements for each object. Here they're going to be connected, right? But then we got these disconnected bags elements. Here, the thing that serves the role of set, but gives this extra power of allowing connections between those elements, allowing structure in these things that an object maps to, rather than being disconnected elements, connected elements that have compositionality. The thing that allows that is by mapping into the double category span. And we talked about that at length yesterday, right? So span is a category where the objects in span are sets. So we're talking about span of set. I should emphasize. You can actually do this with span of other categories. See, here we're strictly talking about span of set. So the objects in span of set are sets. Each object. S is an object. T is an object. These guys here are objects. All these folks are going to be objects. Arrows, the vertical arrows, are functions between those sets. Okay. So having a vertical arrow from object, vertical morphism, vertical arrow from object A to object B says that in this category span of set, says that set A has a function mapping it to set B. Just like our old familiar set that we've dealt with for so long as a category. Pro arrows here. There exists a pro arrow from S to T if there exists some A that has a source map from A to S and a target map from T to S. Or put another way, there's a pro arrow from S to T for each span like this, where we have an A which maps to this set. So A is a set. There's a function mapping from A as a set to S as a set here, and from A as a set to T as a set. And we think of this as kind of A specifies kind of a link almost, where it has a source and has a target, and that intuition is going to be key. So if we have an pro arrow, we went over this yesterday at length in that video, you can find it. If we have a pro arrow from S to T and another pro arrow from T to U, we can compose them via push out to get a pro arrow, a span, from S to U. Each pro arrow is a span. The one from S to T is defined by sum, is associated with sum, specified by sum, span like this, with some A, the map to S, to set S, some set A with a map to set S, given by this function S sub A. So that tells it for each of these arrows, kind of, or this span, this thing in A that encodes a span as a left element from S. It's a particular element for A as a left element from S and a right element from T, right? Each pro arrow, this describes the data for the pro arrow from S to T. We have a span. That's what it means for there to be a pro arrow from S to T, set S to ST, that there's one of these spans with these functions in the set there. So if we have one S to T, pro arrow, and another one T to U, we can use pullback as a result and get something which basically specifies pairs of, as it were, edges going from S to T and then T to U, particular value of T in common. So sort of end-to-end pair from S to T and T to U. And that specifies, this is a span here. If we compose this and compose along that, it specifies itself a span from S to U. It specifies what the A is in the span, as it were, that defines the span from S to U. So whenever we have these spans, we could compose them horizontally. And last time we went over a little bit this mapping of squares. That's going to be less central to our goal here. Okay, so now we're going to dive into why we get out of category. And it's awesome. The first step here is to remember from earlier that Lax double functors, I said it earlier, this is the most basic thing, map objects in D to objects in E. Like a functor, right? Reminds you of a functor. Maps pro arrows, that's an object of D1, to pro arrows in E1. That is true. Okay. And secondly, we're going to remember that in our case, we are examining the very specific Lax double functor, not from D to some category E, but into span. Okay. So we're considering a Lax double functor for our model of a theory means a Lax double functor from D into span. Okay. Remember, it's like a C-set. This is like our double category theoretic souped up version of a set. Okay. Just as we mapped C-sets from a schema category into a set, here we're mapping into the category set, here we're mapping it into span. So we just said objects in D are mapped to objects in span. What are objects in span? Who can say? What's an object in span? We just covered it. It's a what?
Set.
It's a set. Okay. So when we hit it with a double functor X, if we have one of these in D, if in D we have a pro arrow like this, with this is, remember, identity pro arrow, we hit it with the Lax double functor, we get X of X here. Remember, it maps objects into objects, right? X, each of these turns into that, and pro arrows into pro arrows. Here we go. Is this a pro arrow? It's a pro arrow like this, from X of X to X of X. And this is the pro arrow map from this, right? Now, what is a pro arrow in span? Does anyone remember? What's a pro arrow in span? It's a what? A pro arrow in the category span is what? It's a span. It's a span. It's a span, right? Pro arrows are spans. Remember, we just said there's a pro arrow from S to T if there's a span. A pro arrow is a span. So Kevin, brilliantly, and I will follow, will write this like this. This pro arrow going from X of X to X of X, in the pro arrow is called X of U of X, it's a span. It's in one-to-one correspondence with a span. It is a span. That's what the pro arrow means. And these things, just to be clear, in span, X of X is a what? Say it again. X of X is a what? This is
set.
It's a set. This is a set. This is a set, it turns out. Okay. Remember span? Remember in span, this is a set. A is a set. This is a set. This is a set. This is a set, right? So this is a set. And here's our source, and here's our target. Now, this may start to look familiar because notice the left and the right foot are identical. That should remind you of a certain category where you have something up here and you have the same, you have a set here, or it should remind you of a structure we've used a ton in our class where you have a set here, maybe we call it E, and another set here called V, and another one here called V. E has a source. There's a map from E to V, and then another called S, and another one from E to V called T. What am I describing? Where have we seen something like that?
Graph.
graph. This is a graph. This is a graph. We just pull these together. Hey, it's the same thing, right? We could have just as easily written this T instead of showing it this way. We could have bent it around there, right? So it's a graph. These encode the edges. This pro arrow, the map, the image of this map encodes the edges. Remember that? Remember that when we map this over into set, E encodes the edges and X encodes the what?
Vertices.
Vertices. And this is the source of an edge and this is a target. Do you get that? Do you get that point? Okay. So what this is saying, as Kevin points out, is radical. I mean, look, this is saying that, well, at a certain level, you think, well, each object maps into a set, and each pro arrow here maps into a pro arrow here. But look, for every object in D has a pro arrow, an identity pro arrow. I've emphasized that in my coverage in double categories. Every object in our double category has an identity pro arrow and an identity arrow, just like every object in a category of necessity has an identity arrow, right? Identity morphism. So every every object in D has an identity pro arrow. Okay? If you believe that, and you just think about what that means, it means every object is associated with or maps to a set. In other words, the image of that arrow and its pro arrow specifies, a graph. What am I saying? A graph maps to a graph. Every arrow together with its identity pro arrow encodes a graph. What is the edges of the graph? It's the image under this Lex double functor. In other words, the double functor maps this pro arrow into a span whose A is this. This is the A at the top, the apex of the span, right? This guy here kind of for the pro arrow from that object to itself. And this is the set of vertices. This is a set of edges. So every object together with this pro arrow encodes a graph which has edges, the thing at the top of the span associated with that pro arrow. Every pro arrow, when we map into the span, turns into a pro arrow and it has some A on the top, some apex. And that's what this is. And that is the edges of a graph. The object itself turns into a set of vertices when we map it with X. So what I'm saying is every object in its pro arrow, which are all identity pro arrow, always maps to a graph. It's a graph. Okay, you say, wow, it's not a set. Like C sets, every object mapped to a set. End of story. Here, every object which of necessity has an identity pro arrow maps to a graph. You could say, oh, that's kind of cool. It can encode things. It can connect its elements. Before, we just had a sack of disconnected elements, right? We used to get out a sack of disconnected elements. Now we have a graph which encodes connections between those elements. That's pretty cool. But it doesn't stop there. It gets a lot more cool. Okay, so now we have every object goes to a graph. That's cool. It's no longer disconnected. It could be disconnected if this thing is empty, but or the empty set, but generally it has connections between, like maybe connections of a pre-order or something. It says this is bigger, this age group is older than this one, which is older than that one, or what have you. But there's more. Let's map that. So we know that, as Kevin Carlson says, Lex double functors, which encode these models, give every object a graph. Every object in D turns into a graph. That's neat. But let's consider more. Let's put two of these end to end. Two of these end to end. We've been considering this, which specifies graph. Consider two end to end. Okay, look, we hit it with X. Look, objects turn into objects. Pro arrows turn into pro arrows. Kind of nifty. And now let's put these end to end. We turn these things, these are images, of course, from Kevin. We turn it into, we have these two things. Each of these, what is each of these? It's a pro arrow and span. What's a pro arrow and span? It's a what?
Span.
It's a span. So we have one span like this, and we have next to it a span like this, and they hold this edge in common, right? That's what it means in span to have two pro arrows end to end. S to T and T to U means you have these two right next to each other. Do you got that? You got that point?
Yeah, then we
Right,
can use
come-
pullback, right?
Yeah, then we can use pullback. Yeah, you're getting it. Okay. Okay. So we have these things end to end. Now, these things end to end, we can do the pullback of them, and we get some object Q, right? Right? We get an object Q, which describes end-to-end pairs of arrows with a source and a target and a source and target, and where they have the target of the first is the source of the second, right? That's what you remember. That's what we said this means in span, right? C gets pairs of arrows from S to T and T to U where they share a common point in T.
And we have T to U.
Yeah, exactly.
And
Yeah, and so Q is describing end-to-end pairs of arrows here, which are in this graph. In this graph that is the image of this object in its associated pro arrow, we can have end-to-end arrows. So it's saying for each end-to-end pair of arrows, that's what Q is specifying, end-to-end pair of arrows. Well, what about it? Well, look, we have this thing called a compositor, which adds extra structure. And it tells us something really important. It says when we have two end-to-end arrows like this, now this says F, but you can put in X, right? This is F here is our lexible functor. Here, Kevin Carlson is writing as X. So this is X, capital X of X, capital X of Y, capital X of Z, capital X of X, capital. All right, you follow, mutatis mutandis. So this is our compositor. And what it says, look, if you have these end to end, it's not exactly the same as U of X composed with U of X and then hitting that with F. Instead, there's a morphism between them. There's some choice in the matter when you're designing this category. Now, it turns out that we're going to be talking here. We don't need the full power of double categories for this. We're going to assume that the identity pro arrow composes to itself in the source double category. Okay. And what that will mean is that we have M and N. Well, look, I'm just following this exactly. I'm describing this as this, and M is the identity pro arrow, N is the identity pro arrow, and M composed with N, we're going to assume that's just U of. In other words, we're going to assume a less. We're not going to use the full power of double categories. We'll just assume that identity pro arrows compose to themselves. In other words, if you compose it with itself, you get itself. We'll not go into the full flexibility that we could get from a double category. So M composed with X, M is U of X, N is U of X. So in other words, identity pro arrow, we get U of X. And so that's what this is. This is the pro arrow, the lax double functor applied to U of X. There we go. Okay, so what this is saying though is that it's actually a little bit more than that. This and this are a pro arrow. What is a pro arrow in span? It's a what? A pro arrow in span is a span. So what we're saying is there's a mapping for each arrow, pair of arrows. Like like S to T and T to U, there's a map to an arrow. That's what's described by these, to an arrow from S to U. Why do I say that? Because this has to commute. This is a commuting square that's formed by this map here, by the compositor map. So this has to commute. In other words, this pair of arrows, S to T, T to U, if we take the target of the right arrow, it has to be the target of this arrow down here. If we take the source of the left arrow, it has to be the source of this arrow down here. In other words, this arrow is specifying down here is specifying an arrow from S to U for every pair of arrows from S to T, T to U that share that common center point. Every end-to-end end of arrows is mapped into some arrow from the start of the first to the end of the second. In other words, this is specifying a rule for composition of any pair of arrows. That's what this encodes. This rule that you specify for a lax double functor says for any pair of arrows, any pair of pro arrows here, we're going to specify a rule if we have a pair of pro arrows from X to Y and Y to Z, or I said it before, S to T and T to U, we can get a pro arrow in our graph encoded by the object in the pro arrow, or the identity pro arrow. There's some graph. We, of necessity, have an arrow from X to Z, or for my example, from S to U here. So this specifies our rule for composition. In other words, when we specify our lax double functor, we tell it what the compositors are, and we tell it the compositors that encode how to compose arrows. What composed with what gives what. That's what you have in a category, right? You have a guarantee any two end-to-end arrows can compose to some arrow. And when you specify category, you specify what that is within the laws of a category. It has to behave nicely, right? And it's the same thing here. We are specifying with this the rules for composition for turning something that goes from any two arrows end to end in this graph we already said was mapped to by an object in its identity pro arrow. There's some graph. It has arrows between elements, and any two end to end of those is told by this map here where it goes as an arrow from the start of the first to the end of the second. So what we're saying, as Kevin says, is that each object with its pro arrow, which is identity pro arrow, which is guaranteed to exist for every object, we have an identity pro arrow, not only specifies a graph, in other words, the lax double functor hitting it, not only specifies a graph between its elements, not a disconnected bag of elements, but a graph between them, but the edges in that graph are guaranteed to compose. We have a composition rule that specifies how we can compose, the laws by which we compose arrows in this graph. Okay, so that's what we've been going through here, because we are mapping it into category span, in mapping each object in this category D into an object in the category span, which is a set. Each pro arrow in category D goes into a pro arrow in span, which is a span, and spans composed by pullback, and that's what we got here. So we can always get, by pulling back two spans, and we think of them as like going from the first to the second, and then the second one has a source and target too. We could think of Q as the pullback as specifying end-to-end arrows. That's what it encodes, end-to-end arrows. That's why it composes. This composes to be a pro arrow from S to U. That's what this encodes. And for any pair of those arrows, the laxator, the compositor, tells us how to get an arrow, tells us which arrow from the source of the first to the target of the second, we get out. It encodes the rules of composition. And as Kevin says, after you know that, if you studied some category theory, you are just tempted to suspect this thing we're mapping it into is not merely a graph, that each object, because it of necessity as a pro arrow maps to a graph. We saw that, back there from the get-go, right? We saw this. It has the structure of a graph. Now we see it as the structure of a graph where arrows compose, and lo and behold, it's a category. It encodes a category. And the other rules here, so the laxator encodes composition. A span of the identity pro arrow, which he writes, this Evan writes it as ID sub x. We've been calling it U sub x, is morphisms, right? It specifies which arrow goes from what to what. The span here of the object, the set of formed by the objects itself is is going to specify the objects of the category. It used to be the disconnected elements in our sets. And it turns out the uniters specify identities. Not only that, the arrows, vertical arrows, the strict arrows in our source category, when they map over with D, when he hit them by the lax double functor, they turn into maps from the image of X to the image of Y. The image of X of an object, when we map it with D into span, the lax double functor into span, X turns into a category, Y turns into a category. The arrows turn into functors, structure preserving maps between those categories. The pro arrows turn into pro functors between those categories. Okay, now, so how does this work for our case? Well, look, I think we'll just cut to the chase for our case of, where's our nice causal loop diagram example? Where'd my causal loop diagram example go? Okay, here we go. We'll go back to it here. Okay, look, V turns into a set. That is the set smoking or health, commitment to cessation, and smoking, the variables. That's what V turns into, the variables. And in a C set, that will be the end of story, right? It turns into a set of disconnected elements. But here, we know that each identity pro arrow turns into a morphism from some element to which V maps, some object here, to some other. And moreover, we have the ability to compose these things, like smoking to health. We saw, but because of this pullback property of spans, if we have an arrow encoded as the image of a pro arrow here, we have one arrow and another arrow end to end with it, we can of necessity compose them. So here, this arrow and this arrow will compose. Now, if this were merely encoding a graph, and maybe I'll show that case, I'm going to give you these things. This was our traditional C set encoding. Here, all we need is one object and to encode a graph and a identity pro arrow that encodes a graph that is compositional, where we can compose any two end-to-end ones, like this one and this one, or this one and this one. We can encode that. Here, V would turn into the set, when we hit it with the lax double functor, the object would turn to the set ABC, or the objects ABC. This identity pro arrow would turn into the morphisms shown here. There's a morphism so we would turn into a span, and that span would say there are 5 morphisms. The first has a source in A and a target in C. Second has a source in A and a target in C. the second as a source, or excuse me, the third as a source in B and the target in C. That's what this pro arrow here in the theory turns into a span in span, which specifies for each arrow here where it goes, what its source is, that's its left leg, and its target, that's its right leg. Remember, the source and target are both here from the set mapped to by V, from V to V, the X of V to X of V. Okay, and it would have compositionality properties automatically because this is a category. It embodies the graph. It's a composable graph that results. Okay, but how about our case with causal loop diagrams? Here we have a wrinkle. We need two types of links. We need negative links and positive links, and we need them to compose nicely. How does that work? Well, look, the negative links, the positive links will come from this identity pro arrow. That will map into a span where, so right here, this use of X, I call it use of X there, use of V. I should have been more careful. This is use of V. So it has identity positive links from every vertex to itself. We just don't show. Kind of makes sense. As smoking goes up, all other things being equal, smoking would tend to go up relative to the value it otherwise would have had. Yeah, it kind of makes sense. Okay, so we have a set of, the image of this is a set of plus arrows, which happen to here all be hidden. And this one, this pro arrow, which is from V to itself, turns into a span where its left leg is V, its right leg is V, and its apex encodes arrows, and that encodes the minus arrows where they're from. Left leg says, okay, in V, I go from, my source is health, and my target is commitment to cessation. For this minus arrow, it goes from here to here. And this is all nicely mapped out here. And the compositors give the rules. The compositors say, okay, if you have a negative arrow coming, which is the image of this, it's the negative arrows again are from the apex of the span here, X of Q. That is the set of negative arrows. If we have one of them and we have another one of them in a row, the compositor will say, okay, we gives the rules for composition. One of those and one of those composes into a plus. And if we have one from, instead of Q here, we had it from the identity pro arrow, that would be a plus link. And then from one of X of Q here, a negative, we get a negative one from X of Q. We choose as part of the model, just like as part of the C set, you specify some information, what you want it to map into as part of the model. Here, this lax double functor, we give the rules for composition. So we give the rules such that minus and minus become plus, plus minus become minus, etc. That is encoded in these rules, which are part of that lax double functors. So look, we're going to have to finish up here. But the basic gist of it is that we can use a lax double category to encode a theory. We can use a lax double functor. So the theory was something like this, like this. Or like ours with V here instead, and with these pro functors, or excuse me, these pro arrows. Okay, we use a lax double functor from that into span to encode a model, because that gives us the ability to say not only what the objects of the theory turn into as sort of the equivalent of elements, or what they'll be as objects in the target theory, in the target category, but also where for each morphism it comes from and where it goes, or each arrow where where it comes from and where it goes. And it specifies the rules of composition by which those can be composed. The categories created in this way are not double categories, I should emphasize. They are traditional categories. So this is a traditional category encoding our graph. It's not a double category. It's just a traditional one. Here we have the ability to encode structures with greater flexibility. Something that used to require multiple objects, like one for edges, one for vertices, we can do with a single object. And we, in fact, can have multiple types for our causal loop diagrams. We can have multiple types of arrows, like minus arrows and plus arrows, just by having different pro arrows from an object to itself. And we can have rules that observe, that honor the sign, for example, of these. You could imagine another one having a designation question mark that's unknown, and combining it with any other yields a question mark one, for example. So when we have these double theories, we can specify additional information quite readily beyond what we can easily specify for a C set with just like one object. But more than that, we have the compositionality. And that is going to allow us to do homomorphism finding from a theory which might, a model which might have just a single variable and a negative feedback loop. By finding that in this, by doing a homomorphism finding between categories, we're going to be able to find negative feedback loops in categories, regardless of the number of plus and minus arrows we have, because it knows about the compositional structure. It knows if you have a minus, and a minus, they compose to be a minus. Okay, so we have to wrap up now so I can get to this next meeting. I'm sure your head may be spinning like mine was for the first 5 times I heard this, or 6 times or something. But I hope this is starting to give you some sense of what double models look like for double theories. They embody as categories the information. And by doing so with categories, not sets, we can represent relationships between these things that would be disconnected elements. But we get compositionality out as well, which often gives us great benefit, like for causal loop diagrams or regulatory networks, or like for stock flow models. Okay, that's all we have time for today. There is another level of this. We'll talk about it sometime. We may go through some of these examples with more specificity, but hopefully that gets you some basic glimpse of these things. And I would recommend, if anyone wants to go a bit deeper, this one here, and these within Kevin's talk. The entire talk is definitely worth going through. And I think that this talk is also worthwhile. But there's a talk by Evan, which also goes into systematic coverage from one of the Berkeley seminars at a basic level of the different levels of the hierarchy. Okay, gotta go, but hopefully gives you some ideas, and I'll be getting on to my next meeting here with Atri and Huayi. Thank you, everyone.